I'm going to talk a little bit about coherence. So this isn't like an official term. It's just a term that I came up with. But and although I could never find anything in the existing literature that meant what I wanted this term to mean, I have later been told by someone that I came across a week or two ago that this idea does exist in the literature, but I've again forgotten what term it was under. So for now, I'm just going to leave it as this term. What the term means, size-synchrony antagonism, is that you have a trade-off. You have a natural trade-off in systems between the size and their internal coherency, or the synchrony between the portions, the parts of the system. As the system grows, it becomes less synchronous, more asynchronous, less coherent. And this, I posit, is just a fundamental natural law, right? You can't get around it. Now you can manage it, but there is no magic dust you can sprinkle that just lets you get out of it completely. Thankfully, most of the time this doesn't matter so much, because we can design our applications such that our solutions work around this limitation. But I think we see this limitation throughout various fields of endeavor, computer science, physics, biology. Wherever I see systems, as those systems grow, they become less coherent, they become less synchronous. Changes in one part take longer to affect changes in a distant part. And it kind of makes sense when you think about it. In the paper, there is a formal, semi-formal sort of proof of this antagonism principle, but I think it also just follows from if you think about it. Interestingly, JAM presents a new compromise for blockchain systems within this trade-off, within this kind of if I've got a whiteboard, right? Yeah, okay. So we can draw the size-synchrony. So we can grow a system, and we can have it be synchronous, which we all might also say it's internally coherent. And basically, I posit that there is some inverse, like reciprocal curve, such that you can only have systems that exist in this under the curve. Yeah, you can't have something that is really, really big and really, really synchronous. You're kind of stuck going under the curve. And whereas we might see systems that have a big size but low synchronicity, and we might see systems that have high synchronicity but only a small size. So, for example, Ethereum 1 might be over here, right? It's very synchronous, right? Any smart contract can call immediately into any other smart contract that's deployed in the system. The state is totally, in terms of where things are and accessibility, the state is totally homogeneous. Doesn't matter what smart contract you're in, you have total access to all of the state of the system, no problem. But it can only grow so far, yeah, before everything just gets too complicated, yeah? And over here, we might say, well, we can split things out and we can have 10,000 different blockchains, right? Each with their own state, small bit of state. But then this maybe allow the size to grow indefinitely, but they will not be synchronous, they will not be coherent, yeah? We can bridge them, of course, but then those bridges become insecure, There's latency involved. Overall, the system loses its coherency, loses its synchronicity. We can see something similar happening if you look at computer architectures, machine architectures, right? It's not limited to blockchain. Very obvious one is like basic memory, basic processing, data processing. You might have data that exists on the CPU. That's the very, like in a register or in level 1 cache, that's the very, very maximal level of synchrony, but it doesn't grow, right? Level 1 cache is very, very small. Registers, there's not very many of them, yeah? And so in order to grow the system beyond that, we have level 2 cache, level 3 cache, RAM, yeah? But as we go up to the next level and the next level, synchronicity keeps getting less, right? Everything becomes more and more asynchronous. The CPU, if it's only got one thing to do, has to just wait, has to just stall and wait for it to get back to go to memory, read the memory, and get back in. If we outgrow memory, as we always used to back in the 80s and 90s, then we go to hard disk, right? We go to secondary storage, and we have virtual memory. And of course, these days, we tend not to have our data even there. We tend to have our data off on some other computer on the other side of the internet. And if your CPU happens to be blocked on getting that data, and it's going to be sleeping for a very long time. So as we see our systems grow, synchronicity just naturally reduces. We have to deal with it. But it doesn't mean that we are stuck with selecting either here or here. And JAM is, I don't know, vaguely speaking, one of the first blockchain systems that says, well, let's try and imagine a system that sits here. A nice little sweet spot where we get good amount of size, but also a good amount of synchronicity.